Hello, scholars. So we finished up our exploration today of a way we could find the volume of your pie plate or your receptacle by imagining slicing it into infinitely many, infinitely thin cylinders and adding up those volumes. So in the case of a shape where we can slice it in a way that the face of the shape always has, the face of the slice always has the same shape, if we could find a way to write an equation that tells us that area of the face, we would multiply the area of the face by the thickness, and we get the volume of that slice. So I'm not guaranteeing this works for all solid problems, but this is a kind that we can start to get used to. It's one special case where we can for sure find a volume of a solid, and that's if we can write a formula for the area of, I'm going to call it the face of the shape. So imagine taking a slice. If your slice is like a slice from your pie dish in the lab activity from class, then the face looks like a circle, but it has thickness. So another example of a slice, we're going to take slices today that look like squares. Their face is a square, but they're kind of like a Kraft cheese slice, where it's a square with thickness. And we know how to find the area of a square, so we're going to be able to write an expression for area. So in general, if you're going to slice perpendicular to the x-axis, in class you kind of are slicing perpendicular to the y-axis. We're going to kind of turn things around, at least to get started today. We're going to slice perpendicular to the x-axis. Then the thickness of each slice is a small change in x. We're going to imagine integrating with respect to x, and the volume of that slice is going to be that thickness, that small change in x, times the area of the face. So if I want a volume from x equals a to x equals b, I can write this integral. I'm going to integrate from a to b, the area of the face times the thickness of each slice. This is going to be my strategy. I'm going to try to sketch a typical slice. I'm going to try to write an expression for the area of the face of that slice. It's going to for sure require that I know what shape that face has. In class, your faces were all circles, so you used pi r squared, and then times h for the thickness. We're going to see some different shapes today. And we're going to make sure we get the limits right, and we're going to integrate. So an example, I'm going to take this region, which here is called R. I'm just going to clarify for you. I'm going to shade in to show you what I mean R to be. It's this part. So this vertical line at x equals 4, like chops off the edge of R. So that's the area I'm talking about. And I want to take that. It's a little bit silly. We're just getting started, right? There's some kind of solid, some kind of blop shape that looks like R where it hits the ground, and coming up out of R, if I sliced it like perpendicular to the x-axis, every slice looks like a Kraft cheese single. It looks like a square, but it has thickness. So I want to try to write an integral that's going to give me the volume of the solid. So step one, I'm going to try to come in here and draw a typical slice. So a typical slice is a square. So however much of the slice actually would touch region R, which is like the paper cutting board underneath your slice, right? And then it's going to pop up out of the page to be a square. So you have to imagine that square like coming up out of the textbook. So I want to think of a way to write an expression for the area of that square, and then the thickness of the square is going to be dx. So this part you can always, well, for the first 2 years of calculus, I can promise you this is true. If you're going to slice perpendicular to the x-axis, so cross-section implies slicing, perpendicular to the x-axis means I'm going to slice perpendicular to the x-axis. That means the thickness of the slice is going to be a small change in x. You're going to end up integrating with respect to x. Talked about this in class, right? Once you decide what you're going to integrate with respect to, and that's going to help you narrow down your limits. Because this is a dx integral, then the limits on my integral have to be x values. So if I think about the region R, the smallest x is 0, and the biggest x is 4. So I'm going to integrate from 0 to 4. And this is supposed to be a of x dx. I'm going to write that here, but then I'm going to erase it because I'm going to run out of room. So for a slice that cuts into the region R at the place where x equals 2, how would I find the area of that square? Well, I'd have to figure out what this y value is, and that would tell me like the height of my square. And then once I know the height of the square, I can find the area by squaring that. So the question is, what is this y value when x equals, in this case, 2? Well, I have this expression here to tell me that y is equal to the square root of x. So when x is 2, y is the square root of 2. When x is, when x is 4, y is the square root of 4, which is 2. So I'm just thinking about how the x's and the height of the square are related. So no matter what I use for x to get the height, to get the side of the square, that's going to be the height, which in this case is the y, so square root of x. But to find the area of a square, I need to take that side and square it. So I'm going to go back here. I'm going to erase where it says a of x and replace that with square root of x squared. I know that makes you want to say, Mrs. Hicks, the square root of x squared is just x. True. I'm going to show that as a second step. Square root of x. So now, if I want to evaluate that integral, I'm going to come over here and make more room. That's going to be the integral from 0 to 4 of x dx. I'm going to integrate by hand. Feel free to use your calculator to double check it. So it's going to be x squared over 2, evaluated from 0 to 4, and that is 4x squared. So 4 squared over 2, so 8 minus 0. 8 minus 0. So the area is 8. Sorry, did I just say that? The volume is 8. We were finding the volume because we have multiplied area times thickness. So notice the dimensions on square root of x squared would be like distance units squared, and then the thickness is another units squared, so we're going to end up with cubic units. This is an expression for volume. So the volume, 8. 8. All right, so I got another one here. I want to find, well, I have a region R, and I know you guys have seen this one before. That bottom curve is the parabola. So this is f of x. The top curve is g of x. So let R be the region bounded by the graphs of f and g, and if that is the base of a solid, and the slices perpendicular to the x-axis have a face that is square, can you find an expression for this solid, for the volume of the solid? So I'm gonna draw on a slice. I'm just gonna find some place here. I'm gonna imagine a square. I'm gonna imagine a Kraft cheese slice popping up out of the air there, so it's got thickness. And I want to find an expression for the area of that square. I'm going to multiply that area times the thickness, which is dx. And here we can see already my, I said I'm going to have a thickness that is dx, which means I'm integrating with respect to x. My x's go from 0 to 2, so I'm going to integrate from 0 to 2. And the thing I'm going to need to figure out, like, you go ahead and even make up a variable here. Like, I know how to find the area of a square. It's side squared. Well, now there's no s in this problem, so I'm going to have to figure out what does it mean, like what is this side of the square? Now, to have any success, you're going to have to figure out where your square intersects this base that they've told us about. Because when I think about this, I don't have a way to find that distance. But this distance, I can tell that has a boundary at the top, which is g of x, and a boundary at the bottom, which is f of x. Doesn't matter where I take my slice, it's always going to have a side length that has a difference between the g of x y value and the f of x y value. So that's what I'm going to integrate here. This is going to be the integral from 0 to 2. My side, so this is everything is the same except I replace this s with these parentheses, and the side in this case is going to be top curve minus bottom curve, so that's g of x minus f of x. This is quite common for a problem like this. Notice they've asked us to write but not evaluate an integral expression for that, the volume of that solid. So notice I've integrated from 0 to 2, side squared times the thickness. So side squared because that's the area for the face of a Kraft cheese slice. Oh my gosh, are there no examples that are not squares? I got another one here. I have a region R as the base of a solid, and I know each cross-section perpendicular to the x-axis is a square. I'm going to find the volume of the solid. Now, we saw this problem before, and we had this issue where when we were trying to find the area of region R, we noticed that the any rectangles we might draw in this case, their top was natural log of x and their bottom was y equals 0. And then it changes, and over here the top is 5 minus x and the bottom is y equals 0. So we have to figure out how we can split this up so we're still going to be able to write an expression for the area of our square. So you can turn back to your other handout. I'm going to go get my calculator going and figure out what that intersection point is again. All right, so once you know that intersection, we're going to imagine drawing a slice. This slice comes up out of the paper like that. It has a thickness, and it has a side length, which is natural log of x tall. So natural log of x minus 0. And then if I draw my slice over here, and I imagine it coming up out of the page there, that's going to have a side length of my square that is 5 minus x minus 0. So that gives me the idea that I'm going to have to split up my solid into 2 chunks. I'm going to integrate from 0 to 3.693 side squared dx. And then I'm going to have to add the volume that comes from the second chunk of my solid, which is going to be from 3.693 to 1.3065 side squared dx. Now my side is going to be, well, for the first part, I said that the top of this square length was natural log. So this is natural log of x. I could write natural log of x minus 0 to make sure I notice that it's this minus this. And then for this part, 5 minus x. So this is a case where I had to divide the solid into 2 separate parts. I'm going to find the volume of the first part because that first part has a different expression for area than the second part. So final answer, notice again, this one says find the volume, so I would actually go through with my calculator and evaluate this expression. Why don't you come to class tomorrow and we'll practice typing that in your calculator and making sure we get the right result. Okay, check it out. I'm going to make 2 changes on you this time. This time, I still have a region R. It's the base of a solid. And I know this is y, whoops, I don't have my marker up. Y equals 2 square root of x. This time, I've been told that my cross sections I'm going to take perpendicular to the y-axis. And every time I do that, the cross section is going to be like a rectangle. It's going to be more like a Swiss cheese slice than a Kraft singles, right? And what I know is the height is 3 times the length of the base in R. So if this is the base in R of my solid, then however long that is, the height is 3 times. So I have super tall slices, like standing up. So I'm going to need an expression for the area of this rectangle, which I'm going to multiply by the thickness of the rectangle, which in this case is dy. So now I've decided I'm going to integrate with respect to y. I'll make this nice and big. And it means I'm going to have y limits, and here they made it clear. That's from 0 to 6. And I'm going to have to ask myself, how do I find the area of a rectangle? So if it helps you to, I'm just going to model my thinking. It's not that you would have to write this on the test. When I think rectangle, I'm like length times width. And this is a rectangle with thickness, so it's going to be length times width times thickness. And the thickness is already there. That's the dy. So now I'm going to come down to this next line. I'm going to try to fill in what I mean by length and width in this case. So it's going to be the integral from 0 to 6. The length, let's call this part that's in R, let's call that the width. So it's the difference between x equals 0 and x equals whatever that is. Well, I have an expression for that curve, but it's got the y isolated. I need to isolate the x in this equation. So y equals 2 square root of x. Y over 2 equals square root of x. I'm going to square both sides. I'm going to get y squared over 4 equals x. So that's what I'm going to use for the width. Y squared over 4. The dy was already there. And now I'm going to need to fill in something for the length. What do they tell me? That it's, I see now I'm not using the exact same words. They used height and length. I'm using width and length. So to clarify, for width, I'm talking about that dimension that's actually touching region R. I'm going to use this for length. And they told me that that is always 3 times whatever was in R. So I already said whatever was R was in y squared over 4, and I'm going to multiply that by 3. So I have this expression here, which is 3 times y squared over 4 times y squared over 4 again. And again, this is right, but do not evaluate an integral. You just want to make sure you had these correct limits from 0 to 6, and that you'd have a 3 as a multiplier, and you'd have y squared over 4 as a multiplier twice. And then the thickness of your rectangle slice. All set.